Swayam Prabha. Digital India. Educated India.
Let us get started with the equilibrium constant of a chemical reaction, and what I will try to do here, we will work out an explicit example of a gaseous reaction. So example of chemical equilibrium constant of a gas reaction, of a reaction between gases. Consider a simple reaction between gases. The example that I take is basically a dissociation reaction. The reaction is the following. So N2O4, it is dinitrogen tetroxide. It is a gas and it dissociates to 2NO2, nitrogen dioxide. It is also a gas. So one molecule gives two molecules here, or 1 mole gives 2 moles here. So this is the reaction that I would like to consider as an example, explicit determination of an equilibrium constant. So to begin with, we consider that once at a given temperature, we assume that there is an equilibrium for dissociation. So this is a dissociation reaction. The dissociation reaction equilibrates at some point of time, and what happens, we assume that alpha, I start with 1 mole of N2O4 and let alpha moles of N2O4 gets dissociated or undergoes the chemical reaction, alpha moles. So the remaining part that remains here is basically 1 minus alpha remains here, and 1, and that gives me 2 alpha on this side. So 2 alpha for N2O4, and for N2O4 I have 1 minus alpha fraction, and for NO2 I have 2 alpha fraction. So the total mole fraction, in total we have 1 minus alpha plus 2 alpha, that is equal to 1 plus alpha is a total number, is a total fraction. So that means that actually gives a mole fraction for, so for N2O4, mole fraction is 1 minus alpha by 1 plus alpha, because there is a total number of moles here, and this is mole fraction for NO2 is 2 alpha by 1 plus alpha. And that means that the partial pressures for, so partial pressures for N2O4 is 1 minus alpha by 1 plus alpha times P. If P is the total pressure. If P total pressure, and for NO2 we have 2 alpha by 1 plus alpha is the mole fraction times P is the partial pressure. This is the partial pressure for N2 and this is the partial pressure for N2O4. Now we know the equilibrium constant. Equilibrium constant is what? Equilibrium constant Kp, that is basically we know the partial pressure of the product raised to their stoichiometric coefficients. That means here you have NO2, P of NO2 to the square divided by P of N2O4, and P of NO2 is the basically, this is my P of NO2 and this is my P of N2O4 and P of NO2. So this means we have 2 alpha by 1 plus alpha square P square divided by this quantity, that is 1 minus alpha by 1 plus alpha to the power P. This should be the ratio, and so Kp, we rewrite it as 2 alpha 4 alpha square P square by 1 plus alpha whole square times 1 plus alpha divided by 1 minus alpha times P. So this gives me 1 plus alpha here. So 1 plus alpha into 1 plus alpha, 1 minus alpha square. So this is 4 alpha square divided by 1 minus alpha square times P. P cancels out. I have only one P here. So Kp is basically this quantity. So Kp is 4 alpha square by 1 minus alpha square times the total pressure of the gas. So this is my, this is the equilibrium constant for this chemical reaction. Now the point is how to determine this alpha. That has to be specified, otherwise this becomes difficult to handle. So we know, we again take resort to our ideal gas laws, and this tells us that to determine alpha, that is a mole fraction. So I have the total number of moles is, we know that employ PV equal to N RT. N is the number of moles. N is the number of moles. So how many number of moles are here? So, let us start from N0 moles of N2O4. N0 moles of N2O4 means then I have the total number 1 plus alpha into N0 must be the total number. So N is basically 1 plus alpha times N0. And you know that N0 can be determined easily if we know the total weight of N2O4 divided by molecular weight of N2O4. So this will give me my NO. So that is simple. But NO times I will have to take care of this 1 plus alpha because that is the total number of moles at equilibrium. So at equilibrium, because the gas law actually operates at equilibrium condition. So since this is pertain to an equilibrium condition, so this must be at equilibrium. But N0 is the number of moles, the initial number of moles, start from. That is N0, the initial moles with which we started. So take care of the fact that this is basically an equilibrium condition specified by PV equal to nRT, but N is now basically 1 plus alpha times N0 at equilibrium. So PV equal to 1 plus alpha times N0 times RT. Now what you do, we determine what are the things to be determined. Determine P, you can determine P, V, N0 and T. So this side and both this side is determined, and then this fixes my alpha. So I can determine this alpha in this way. So that's the way we find out this this Kp. That means Kp can be determined by alpha, and P is the total pressure that we know. So if I can measure the pressure of the gas and determine the volume and the temperature is known, everything is known, and we can find out how much weight we N2O4 with which started. Then I measure this alpha, that fixes my alpha, and that alpha gives me this Kp. So that's the way we determine this thing. Now, interesting thing is to consider how the pressure affects the chemical reaction. How pressure affects the dissociation. For this, a simple thing would be if I rewrite this equation, that rewrite Kp equal to 4 alpha square by 1 minus alpha times P. This means I have 1 minus alpha, or this is Kp minus Kp alpha, alpha square, and that is equal to 4 alpha square P. So that means if I determine my alpha, so I can write this alpha as Kp. So alpha square is basically, if I take it to this side, so I write Kp4 or alpha square into 4p plus Kp equal to Kp. So I take this on the other side, I take alpha square common, so alpha is 4 p alpha square times Kp, and that gives me Kp. So alpha is basically square root of Kp divided by Kp plus 4p. So this means what? That if p tends to 0, so this is a very simple condition. So if your pressure tends to 0, you decrease your pressure, then what will happen? If decrease your pressure, this alpha goes to 1. Alpha goes to 1 means what? Alpha goes to 1 means this is 0. So N2O4 gets completely dissociation. So reaction is highly favored. So reaction or dissociation is highly favored. So when you reduce the pressure, that will help the reaction. But if you increase the pressure, P goes very large, goes to infinity. So if this goes very large, so Kp by Kp, so that overwhelms this Kp, and this alpha goes to 0. This is infinity. Alpha goes to 0. Then what happens? The reaction is not favored at all, and the reaction proceeds in the opposite direction. So the dissociation is highly hindered. The dissociation is so this is a conclusion that you can also make from your idea of the application of the Large-Chartelier's principles, which says that if the system is at equilibrium and if you change one of the parameters of the system try to readjust in a way that nullifies your action. So that is something that is also contained in these statements. And so this is basically a reflection of the Large-Chartelier principle in a general form, but in a more quantitative way. And this reaction is a very simple illustration by which we can show that this can actually, how pressure can affect the dissociation or affect a chemical reaction. And there are many complicated cases that is possible, and where such a simple-minded application might not be applicable. Simple-minded approach might not be very much well suited, but in those cases we'll have to consider other details. But for the time being, we will stop this topic up to this point, and then now we'll go over to other aspect of the chemical reaction, that is how this is to show how the equilibrium constant changes or varies with pressure, but it is also a function of temperature. How does an equilibrium constant changes or varies with temperature? That is another aspect that is important for all thermodynamic consideration. So we will try to see that thing now. So how temperature or this is basically a, I should specifically write an equilibrium constant, how it is affected by, it is better to write how reaction an equilibrium constant constant by temperature. So we are talking about equilibrium constants and see how it is actually affected by temperature. So we know how to express equilibrium constant in terms of the standard free energy changes. So the condition is the equilibrium constant and in relation to the equilibrium, in relation to free energy change is basically delta G0 equal to minus RT log of this equilibrium constant. So K is the equilibrium constant. That was the, so K is the equilibrium constant. How does it affect, how does this temperature affects this reaction? So if I write that what is d ln K dt, that is my question. So d ln K, how it is changing with temperature. So that means we have to consider 1 by R ddt of delta G0 by T. So I can rewrite this equation in this form, that I want to know this side, that is how d of ln K changes with temperature. So that is that. So this equation can be rewritten in this form. And the next question is, what is this delta G0 and by T and how it is affected? So if I want to calculate this quantity ddt of T by T, let us see what this quantity is. Then we will find out my delta G and then 0. So let us see what this quantity is. Then it is, I can write it, del is 1 by T del G del T minus 1 by T square, that is G by T square. Now what this quantity is, dG dt, we know that dG, we know that from the definition of dG, that you can express as V dP minus S dt. You get this relation simply from the definition of this free energy, gives free energy, and you take the differential and you apply the first and second law combination. So if you do that, you will get this relation. So that means that del G del T is effectively P, that is equal to minus S. So del G del T is basically, I can write it as minus S by T here minus g by t square, and that is equal to minus ts plus g divided by t square. Now what is this quantity? We know from, since g equal to h minus ts, then g plus ts is equal to h. So this is nothing but h. So it is minus h by t square. So delta, so ddt of this thing is basically minus delta. So if we take the difference, so it would be dd t of delta g by t. If we put a 0 here, so it would be minus delta h 0 by t square. So this automatically, so if that follows, then we know that ddt of this is now determined. So you have d ln k dt, that is equal to, there is a minus sign and minus signs, they cancel out, and we have delta h0 by rt square. So this is the basic equation by which we can understand how the chemical equilibrium constant changes with temperature, and that depends on your delta H. So delta H is a change, is the enthalpy change in the standard state. So 0 actually is assigned for the equilibrium values that we know, delta G0. So here also delta G0, delta H is, which is superscript 0 is there. So that's the thing. And if we integrate this quantity, so what we get is, if we integrate, so it is d ln k equal to delta h0 by r. Then we integrate from some t0 to t 1 by t square dt, and that is ln k equal to some delta 0 by r with a minus sign, because 1 by minus t, and this is 1 by t minus 1 by t0. So this is plus a constant. So to take that in that constant, and so ln k has something to, if you plot this, so it is basically the two terms, that is minus delta h0 by r into 1 by t plus some term delta h0 by rt0. So this is a constant term, sum. So if you write it as y equal to mx plus c type of plot, so ln, so if I plot ln k as a function of 1 by t, then I see that there is a slope here minus of this kind, and the slope determines my delta h0. So slope determines delta h0 by r, and that gives me the enthalpy change for the chemical reaction. Enthalpy change for the chemical reaction. So I can find out how the reaction is affected. Another straightforward thing you can derive from this equation, that if delta G, delta H is negative for exothermic reaction, heat change, that is delta G, is less than 0. So the equilibrium constant is decreased. That means the reaction is not really favored. That so it cannot really proceed towards that direction for exothermic reaction. So ln K or K itself, if I can write, increase of temperature. So on the other hand, for endothermic reaction, delta is 0, is greater than 0, and it is, so it is, the conclusion is just opposite. K increases with increase of temperature. So this is again a conclusion that we derive qualitatively from the La Chatelier's principle, which says that if you change any of the parameters of the system at equilibrium, the system will move in a direction which will to nullify that particular effect. That means, so if you have an exothermic reaction which produces reaction, so that will be opposed. That reaction will be opposed with the increase of temperature. That will not be favored. But for the endothermic reaction, it is always helpful if you increase the temperature. But this should be taken purely within the domain of thermodynamics. This has nothing to do with the rate of chemical reaction. It is just how the equilibrium constant or the yield actually changes. So that is the main concern for this equation. It is not that how much is produced in a given time interval. That is a part of that is a concern of chemical kinetics. So it is purely from the thermodynamic argument we can show that exothermic reaction is not favored by increase of temperature, and while the endothermic reaction, it is really helpful. Increase of temperature is really helpful. So with this, I conclude my part on discussion on chemical equilibrium, and next lecture we will move on to phase equilibrium, another type of equilibrium which are important, and we'll go over to phase equilibrium problem. So thank you all for your attention.